I'm going to discuss flow measurements today. Um, what you see here is a cross-sectional area of a pipe that is blocked by this device, as you can see right in the middle. And my intention here is to demonstrate how we can actually measure the flow, let's say, pass through this opening in this pipe. So water is flowing through here. Okay. Of course, I got to switch it to the appropriate brush here. So the water is going through this pipe. Okay. If this is the symbol of water, it's going to go through our opening. Again, I'm trying to demonstrate how the water can actually flow through this pipe. And for that matter, this doesn't necessarily have to be water. It could be really any kind of a fluid. It could also be gas, because as you know, gases are also fall under the category of fluids, except that they are compressible, whereas water is an incompressible liquid. So that could also be used as such. So if we would like to measure what would be the flow rate through this opening, if you guys have any questions about what a flow rate is really nothing but the quantity of a fluid past a certain point, in this case through our little gate. It could also be within a pipeline that I just draw the cross-section area, or it could also be an open channel flow. That's also a possibility, and that also can be measured by the same type of principles. Of course, there'd be some differences. So the flow rate here is measured by Q, and for this opening, of course, we're going to have a certain cross-sectional area here. Let's call that cross-sectional area A. Okay. And also, we're going to have the time that's involved. Okay. And there are also the speed of the fluid that goes through this point. So these are all the factors to consider. The factor of time, since we are talking about one point, then we assume that t is instantaneous, 0 at any time for the sake of our discussion. So this would be actually would zero out. So this would be 0. Okay. And then I'm left with A and V. A is the cross-sectional area of the opening, or the pipe in this case. We're talking about the opening, so A would be the cross-sectional area of this opening, and V would be the velocity of the fluid that passes through this particular point. Of course, as we reduce the cross-sectional area from upstream to the opening, or the obstruction that we cause here, the pressure and all that would be different. A would be different, and velocity is also could be different. So what we try to do here is really try to simplify the measurement. So knowing that the velocity of the flow would be V, and then the measurement that we call that in order to measure the flow, simply we show that as Q, and Q would be nothing but A multiplied by V. So this would be the flow rate. Okay, the unit as such for this, as you can imagine, the unit could be either, you're talking about a volume, so it could be cubic meter. I'm going to just spell it out. Cubic meter over, it's going to be cubic meter divided by, we're going to be cubic meter, since we're talking about area. Better yet, let me just spell this out. The cross-sectional area would be square meter, right? So it's meter squared multiplied by, and I show multiplication by a simple x here, multiplied by, what's the velocity? It's per second, right? So meter per second, so the result unit-wise it would be what? Cubic meter per second, right? I think that helps you more to understand the unit. So that is really the unit, so I'm going to spell it out here to show you the units. Okay, so this would be the pretty much the flow rate. Now the question that we have here is that since the rate would be, there would be somewhat a fluctuation, we're dealing with a fluid. The V that I just discussed here is the average velocity. The cross-sectional area is pretty much constant, and the Q would be really the average flow rate. So this flow rate is calculated using the average flow velocity and the area of the pipe. So what is the mass flow rate? The mass flow rate is nothing but this quantity that we just looked at, Q. So then mass flow rate is rho, which is, I'll just show you as RHO multiplied by Q. I don't have the capability of showing some of these symbols here, so I simply put rho times Q, and that will be the mass flow rate as such. So it may be possible that we're interested in an additional quantity, and that's really used in many pipes and channel flow situations, and that is the pumping power, in case you would like to provide a pump to pump the water or the fluid through the channel or through the pipeline. As such, we define pumping power, PP. We define that pumping power. Or nothing but PP. And it's actually capital P, which is nothing but Q that we just calculated. Of course, it's going to be capital Q multiplied by delta P. Okay, so this is the pressure change across the device. So if we would like to define an extra quantity that's of interest to different type of situation, and that's called pumping power. It's defined as the flow rate multiplied by delta P. And delta P is nothing but the pressure change across the device. So it's a pressure differential, really, that occurs across the device. We may have, again, as I mentioned to you, we may have a different scenario here. It's going to be a different P, and it's going to be, of course, different cross-sectional area, and it's going to be different P, and it could be different upstream, downstream, and right at the opening where the flow is to be measured. So this is really the bulk of what we would be used for some of our measurements. So what would be the unit of pumping power? As you can imagine, it's going to be knowing that the Q would be cubic meter per second. Then delta would be the unit of the pressure. So for this, if you want to find the units for the pumping power, the units would be as cubic meter per second multiplied by Newton per square meter, because that is all the units that are associated with the pressure, this one, and the unit that's associated with the flow rate, cubic meter per second. So that would be the unit. We can also express that as joule per second, because in Newton meter, if we look at this end result of this multiplication, and it's going to be also J per second. Okay, so that would be the units for that. Okay, so how can we calculate the velocity? We can do that in multiple ways. We can use any type of pressure measurement. Let me bring this back up. Something happened here now. Okay, so I scroll it back up. Okay, so okay, good. Okay, much better. So in order to calculate the velocity, we can use different ways. We can calculate the velocity in many ways, including the use of a pressure measurement. We've seen that last time in previous lectures. We also did some solve some problems on that. Or we can use really any method to measure the velocity. Now, there are also more to our discussion, and that is some of the devices that are used to actually calculate the flow itself. There are several examples of flow meters: the nutating disc flow meter, there are rotary vane flow meter, there are loop impeller flow meters, and so on. You can pretty much refer to the handout, the course notes, and refer to book for more information on some of those flow meters and so on. So the class of flow meters that are pretty common is what we call the flow obstruction devices, or flow obstruction flow meters. So let me take a look at that now and discuss that with you. So flow obstruction devices. So they come in different forms and shapes. There's a type that are presented here. These are different types. I'm going to show you their shape to you shortly. So an example of this kind of devices is shown here. If I can get it to work. There we go. Okay, here's an example of an obstruction, a flow obstruction device. And before we talk more about the obstruction, the flow obstruction devices, let's talk about a flow as such that's shown here, what we call the one-dimensional flow system shown here. And let's talk about the situation here. Upstream we have P1, T1, rho 1, A1, meaning that the pressure, temperature, density, and the area of upstream, it could be different than the pressure, the temperature, density, and area of downstream. It's important to realize that. And of course, in cases in which any of these quantities are the same, for example, if the device is not long enough, then there will be no temperature across, because the temperature is kept constant, and then T1 and T2 is the same, and the effective temperature is going to drop out. The same thing with density. If the density of would be the same, then of course that would also would not be a consideration for the situation. However, the continuity relation would be valid. Let me bring that in. Okay, so this is the continuity. I can't really show it here. It doesn't really work well here. So the continuity consideration is shown here. So for such a situation, as you have just seen, we're going to have this. I'm going to overlay these two, one over another, to show you, illustrate the point. So the if this is a one-dimensional flow system as shown, the continuity relations for this situation is shown here. The M, which is what we call M dot, would be rho 1, A1, U1. It would be rho 2, A2, U2, where U1 and U2 is the upstream and downstream flow. So if we can expand that equation, U would be the same as the V that we just discussed. So it could be U2, or it could be V1, and it could be V1 U1 or V2 U2. So if we use the same principle, the famous Bernoulli equation from fluid mechanics, then the equation that's shown here, P1 over rho 1 plus U1 squared divided by 2 G sub C, that would be equal to P2, P sub 2 divided by rho sub 2 plus U2 squared divided by 2 G C. This is really a Bernoulli equation that is really not a magic. The equations are well established. The principles are well established by Bernoulli, and you can really find it anywhere. So in our case, since the density is the same, then rho 1 would be equal to row 2. In our situation, what's different is the U1 and U2. We're going to solve these equations simultaneously to get the difference in the pressure, these two equations. So what we are going to do here is we are going to pretty much calculate for the unknown here, and we plug them in to that equation. There are two unknowns, two equations, so we can solve it simultaneously, and we would do a substitution, and we're going to get to this equation. P1 minus P2 is U2 squared rho divided by 2 GC multiplied by 1 minus quantity square A sub 2 divided by A sub 1. Okay, so what we really do, the physical meaning of this equation is we take the ratio of the area of the cross section. So A2 would be the ratio of downstream. We would divide that by the ratio of, we would divide that by the area of the cross-sectional area of the upstream. So A2 divided by A1, it gives us the ratio. What is the ratio of the area of the pipe downstream over the area of the pipe upstream? That means if, obviously, if A1 is greater than A2, that means if you look at this ratio, A2 divided by A1, what happens here if A1 is greater than A2? Obviously, A2 divided by A1 in that case would be less than 1, right? If A2 is the same as A1, that ratio would be 1, then P1 minus P2 would be 0, right? Because if A2 over A1 is 1, then this would be 1 minus 1. This would be 0 inside the bracket. And the rest of the equation would be 0. And as such, P1 minus P2 would be 0. But if A2 is greater than A1, then this quantity, A2 divided by A1, would be larger than 1, right? So I'm subtracting something that's larger than 1 from 1, okay? So then this would be a negative number, right? P1 minus P2 would be a negative number. So there would be the pressure decrease. The pressure would decrease. Now, if A1 is the first situation we discussed, if A2 and A1 is the same. Second situation, if A1 is greater than A2, or A2 is greater than A1, and that would make this to be greater than 1. We subtract a number that's greater than 1. It's going to be a negative number, and remember that the square is, we're only squaring the parentheses, not the bracket itself. Now, what if this ratio is smaller than 1? Okay. That means in order for this ratio to be smaller than that, A1 must be greater than A2, as in this case. In our case, A1 is greater than A2, or A2 is smaller than A1. So if A1 is greater than A2, and this ratio would be less than 1, right? The ratio is less than 1, and then we are subtracting. We square that, we're subtracting something that's less than 1 from 1, and we will see that P1 minus P2 would be a positive number. Okay. Okay. So this is really what this equation means. And then we can do again another manipulation to this equation. We are going to put that back up to, as you remember, we talk about the flow. If the volumetric flow is shown as Q again, the volumetric flow at cross section 2, we're going to equate that to A sub 2 U sub 2. We've seen this equation already. It's going to be A sub 2 divided by square root of 1 minus parentheses A2 over A1. Again, we take that ratio of the area at 2 by the area at 1, depending on if this quantity is larger or greater or smaller than the A1 is greater than or smaller than A2, or if it's equal, then the whole scenario would be different. So that's really how we do this type of calculation. Again, we spell out all these equations here and the terms here. Q is the cubic feet per second, or cubic meter per second. A is the area, square meter or square feet. Rho is the density. It's either kilogram per cubic meter or pound mass per cubic feet. Pound force to show the pressure. Pound force per square foot would be the unit for the pressure. And G sub C is the gravity, acceleration of gravity. In this case, it's different than what we use as 9.81 for the gravity of Earth, acceleration of gravity of Earth. So it's somewhat different. This is 1 for 1 kilogram meter per Newton second square, and 32.17. It's the pound meter foot pound of force. So please keep that in mind. Could be a little bit complicated, these units, but really the bottom line is if you follow them and make sure you understand them, then you would not run into any problems. Okay, so we have this equation calculating Q this way. Again, in this equation, the pressure differential is presented here, P1 minus P2, multiply that by G sub C, and we take it from there. So it is very interesting to note, as many of you guys that have worked outside academia, you would know that the ideal Q that we just calculated based on Bernoulli equation is actually never the same as the actual. So there would be some variation to that. The reason for that is there are many parameters involved here, and that would affect the discharge, and obviously not all of them could be considered and discussed here. We only talk about the ideal situation. As such, in order to calculate the actual Q, we need to multiply the ideal Q by some kind of a coefficient called discharge, the coefficient shown by C. And as such, the actual Q over ideal Q, the flow rate, the actual flow rate, the actual volumetric flow rate that I interchangeably use here as flow rate, divided by an ideal volumetric flow rate, Q ideal, would be C, and that's the coefficient of discharge. There are graphs and other methods that are available in which we have the discharge coefficient. We simply multiply that C and the discharge coefficient by ideal Q that we calculate from these equations to get an actual Q. So the discharge coefficient is not a constant, and again, it depends on the geometry of the channel or the pipe and the Reynolds number. And so again, this could be both for the liquid and gas flows, and of course liquids are considered incompressible. I show it here as a capital. I can also highlight it here, underline it here. Okay, and this actually should be I here, incompressible. That means they have a constant density. The density won't change, and of course, the density for a compressible fluid can change with pressure, and this is the principle of hydraulic systems that we use here. We take advantage of the incompressibility properties, and as such, we would use them to our advantage to increase the pressure, and it would achieve great results. They're used in every car, every actuator. They're hydraulic actuators, and they're used in many, many different applications, the cranes, lifts, what have you, mostly mechanical systems. So if the flow is incompressible, in case of liquid, then for different types of obstruction devices, obstruction meter devices, then we would have different equations. But in all these equations, certain parameters would be different. Now, the three cases that I show you, A, B, and C, that you just saw the graph on, each of them are different. They show different types of obstruction. I'm going to bring you back to that figure again. I think I show that figure further down here. There we go. As you can see, there are three figures shown here. I'm going to reduce this a little bit so you guys can get the picture. Okay, so this is the three types of obstruction meters. They're pretty typical. The first one, A, is the Venturi. The part B is the flow nozzle, and so Venturi, nozzle, and the third one is the orifice. So you want to make sure you guys know the difference between the three. So the top one, A, is the Venturi, the B is the nozzle, the third one is the orifice. So I mentioned that because we are dealing with different equations for each situation and so on. So if we have Venturi, Q would be C multiplied by M, and I'm going to define these as what C and M is. You know the A sub 2 is the cross-section area at point 2, P1 and P2 is pressure differential, rho is the density, so the only thing that you may not know at this stage is C and M. If it is a nozzle, an orifice, then Q would be K multiplied by A sub 2. So as you can see, this portion of the equation remains the same with the 2, okay, right? And what's different here is C multiplied by M. These two portions are different, okay? And the K, as you can see. So what's an M? Again, M is what we call the velocity of approach, and that velocity of approach factor is, again, a ratio. We try to calculate this ratio as, again, the ratio of A2 over A1 squared. We subtract that from 1. We take the square root, and we take the inverse of that. So it's 1 over 1 minus A2 over A1 squared. And then the discharge coefficient is called C here. Again, this discharge coefficient are calculated from the appropriate table. And again, this coefficient will be different for different situations. K would be, capital K would be the flow coefficient. Again, and that is a variable, and it can be found in appropriate tables and plots. And K can also be calculated as C multiplied by M. So this is very interesting to note here that C multiplied by M is really nothing but k. However, for Venturi meters, it's more complicated. So instead of having one parameter k, we have two parameters that are multiplied by one another. The question that some of you guys might have is why do we have so many of these parameters, and why do we have so many of these coefficients here and there? Well, the reason for that is again, from the ideal situation to an actual situation, there are many variables. Theory tells us that we can, ideally calculate the discharge or the quantity as such, but in the lab, that's not really possible. And even if it is possible in the lab, labs are a controlled environment. The actual situation could be different. So based on many tests that were performed and later on compared with the theory, it has been shown that we need to adjust using these parameters, and that's exactly what we're doing here. So Reynolds number is defined here, as you can see. So far, probably you've had a question about that. Okay, so both C and K are functions of the Reynolds number. Reynolds number defined here as the dynamic. It defines as the ratio of fluid density multiplied by mean flow velocity, and I can point to it as I'm going to go over this. So this is the top portion of it, and there are three numbers there that are multiplied, or three quantities of fluid density, the mean flow velocity, and the diameter at a particular section for which the Reynolds number is specified. There are many mistakes associated with calculating the Reynolds number, and that is simply associated with D, because it's very important to realize that the Reynolds number is calculated for the particular section for which it is specified, because it varies. And we divide that rho times U sub m times D, we divide that quantity by the dynamic viscosity. So what we are doing really here is that we are taking the ratio of this quantity and call it Reynolds number. Okay. So what if we are dealing with compressible fluids? In that case, the situation would be a little bit different. There's an expansion factor called Y, and we are going to use that expansion factor. As you can see, this is very similar to what you've already seen, except this Y would be different. Here, again, that would be different. And how we can calculate Y, and that's seems a little bit more complicated, but it is really not when we look at this equation and understand the meaning. So we are going to use this equation. In this equation, the only thing that you haven't seen so far is the gamma. The gamma is nothing but the ratio of C sub P over C sub V. And C sub P is the heat capacity at constant pressure, and C sub V is the heat capacity at constant volume. They are given for different situations, and we use them to our advantage to calculate gamma. If we are using this equation for orifice, again, we are bringing in Y1. Y1 would be a little bit different than Y, so we simply, instead of calculating a Y here for Venturi and nozzle, instead of using Y, down here we're using a Y1. So the only difference here would be Y1. And Y1, again, calculated the way you can see it. Again, in this equation, everything is known. P sub 1, P sub 2, A sub 2, A sub 1, gamma, which I just discussed, C sub P divided by C sub V. There are also other types of flow meters, including sonic nozzle, turbine meter, anemometer, thermal mass meter, and magnetic and optical methods. Again, we leave those for a more advanced courses. Try to cover the basics here, and as you can see here, that by itself it could be quite a challenge. So if you have any questions, as you know, please feel free to contact me, and I'm going to provide you with my direct email address again. That's the best way to get a hold of me, because my other email may not work at times. So let me just for questions, please contact at Daytona State.edu. I hope I spell it correct. That brings me to the end of today's discussion. Thank you for your attention.